Hey everybody, so today we're going to talk about probability, which will be our last sort of silo before we get into statistical inference, where we'll cover various analytical approaches to test the relationship between different types of variables, whether that's quantitative to quantitative, qualitative to quantitative, qualitative to qualitative, or qualitative to quantitative. Before we get started, I have one announcement. I sent out a survey to the class. This is different than your spot survey, which you'll be filling out for evaluation purposes. This survey presents you with the opportunity to give me feedback that I'll then incorporate into future lectures for the remainder of the semester. So thank you for those of you who did fill that out, and I hope you can all leave some feedback for me on there. As I mentioned, we'll be covering probability. We'll start with some basic definitions that you need to be familiar with before moving on to complicated sections of probability and statistics. And then we'll go over a few relationships between events, which we'll cover shortly. So you've seen this image before in early lectures. This is kind of my depiction of the difference between statistical inference and probability. So in inference, as you've seen, you start with a sample and use statistics to make inference about the general population, which I'll sometimes refer to as the truth. Probability works exactly the opposite way, where you know the truth and you want to know what's going to happen in your sample. So I have a question for you. Can you predict what's going to happen in your sample if you know the true probability of an event? And I want you to consider the examples listed here, like rolling a die or flipping a coin. Let's just assume that I have a fair coin. I know it's 50-50 chance of heads or tails. Can I predict what's going to happen in my sample by knowing that true probability? And then I have a related question, and I think a deck of cards is a better explanation for this question, which is, if I've seen the first draw from a deck of cards, can I predict what's going to happen in that second draw? And don't worry if you're unfamiliar with this concept of independence. We will be covering that later on in this lecture. Let's take a minute to think about those two questions. So let's start with the true probability. And there was no right answer to these questions. I think it is subject to interpretation. But when you know the true probability, as in a fair coin, can you predict what's going to happen in the sample? The answer is somewhat. I can't tell you what's going to happen on the first coin flip, right? I know it's a 50% chance of heads and a 50% chance of tails, but that does nothing for me in terms of the realization, right? It's going to be one of those two things, but I don't know which of the two. And in fact, they're equally likely, so I can't even make a guess as to which one's more likely to happen. However, as the sample size increases, I expect to have about 50% heads and 50% tails. In what order they appear, I couldn't really tell you, but I know that as the sample size increases, I will have an even split between heads and tails. Similarly, with does past observations or realizations from an event help me to predict what's going to happen in the next event? It really depends on this concept of independence, which we'll cover later. In the case of a coin, absolutely not. A fair coin, what happens the first flip does not tell me what happens the second flip. In fact, that's known as the gambler's fallacy. They'll say something like, well, the coin came up heads this time, and I know it should balance out to 50-50 overall, so it's going to come up tails this time. And that is absolutely not how probability works. If two events are independent, like a coin flip, what happened in the past has no influence on what's going to happen in the future. However, with the example I gave you with a deck of cards, the events aren't quite independent. It's still very difficult for me to predict what's going to happen because there's 52 different cards in the deck. The first draw, however, does limit the space of possible values for the second draw. Still makes it very difficult to predict what's going to happen, but it gives me some information on what that next draw could and could not be. So we'll go more into this concept of independence, but whatever your answer was here, hopefully the intuition behind it was correct. The simplest way to answer this is that knowing the true probability doesn't help me to identify what's going to happen in my sample. Although it does give me some information, it doesn't tell me exactly what's going to happen in my sample. And similarly, knowing past observations doesn't tell me what's going to happen in the future, although it does provide some helpful information. So to understand probability, I think the first concept that we need to go over is a sample space, which is exactly what it sounds like. It's the space of all possible outcomes that you may see in your sample. And then as a side note, I also wanted to introduce this word, an event. You'll hear people talking about events a lot. This is a collection of outcomes. It could just be one thing, or it could be many things within the sample space, and that is sometimes called an event instead of an outcome. So I want you to think about the sample space for these different types of experiments. A dice roll, your grade and your grade in this course. Take a minute. Let me know what the sample space for each of those events looks like. So for a dice roll, it's any of the numbers 1 through 6 inclusive. So that's 1, 2, 3, 4, 5, 6. Those are all possible outcomes of a dice roll. If you really wanted to be specific about it, I guess there's like a small chance it's perfectly balanced on a point and doesn't land on any number. But most dice are made fair so that would not occur, and it would always fall on a flat side. Your grade on this course, you could have thought of as the numbers 0 through 100 inclusive, or you could have thought of as the letter grades, which is A, B, C, D, E, F, plus or minus, I believe. And what would events for each look like? Again, these are just a collection of possible outcomes. So an event for a dice roll could be something like I roll an even number, or it could be even simpler, like I roll a 2. And I know rolling a 2 is also an outcome, but you could think of it as an event, because as I mentioned, an event could be just a singular outcome. Similarly, for your grading in this course, you could select a range of values or a specific number or letter. Those are examples of events. So to again review the definition of a sample space, it's a collection of every possible outcome. So I want you to think, what's the probability of a sample space? I know this notation is new to you. We're going to go over it in the next slide, but this is just saying what's the probability of your sample space. So we haven't even gone over the rules for probability. We're going to do that in the next slide. But as you'll see, it ranges from 0 to 1, and the probability of something in my sample space occurring has to be 1, right? Because it's going to be one of those possible outcomes, because the sample space includes every single outcome. So something in my sample space is going to occur every time. The probability of something in my sample space occurring is 1, or 100%, however you want to word it. So probability, which will sometimes indicate with the letter P, is also known as likelihood. You may hear people refer to that, although usually when they're talking about likelihood, they're talking about multiple events. It is synonymous with probability, and as I mentioned before, it ranges from 0 to 1, and hopefully this is all a familiar review to you. The larger probability, the more likely an event or outcome is to occur. And what does a probability of 0 or 1 represent? Hopefully you know that 0 means absolutely an event is not going to happen, and 1 means it's a certainty. Just like in that example we went over with the probability of a sample space. And here I'm introducing that notation that we just used, where event X the probability of event X is written as P, and then in parentheses, the event's associated letter. Okay, so that's some background that's going to be helpful now to go over a few concepts related to probability. First one we're going to talk about is a complement. And I think one way to remember this is, you might have heard somewhat of a joke, somewhat of advice, that a complement is when two things complete each other. So the complement of event A is, one way to think about it is not event A. So if this is my sample space, this is the range of all possibilities. Here's event A. Not event A is everything outside of it, so everything in gray. And the two things, event A and the complement of event A, make up the entire sample space, so they do complete each other. So how would you calculate the probability of the complement of event A? And this is the notation for writing complement. How would you calculate that? Take a minute to think about it. Well, we know the probability of the sample space. This is your big hint. We talked about that a couple slides ago. The probability of the sample space is 1. So if I know the probability of event A, to get the probability of the complement, I'd simply do 1 minus the probability of event A. Okay, now I want to talk about dealing with multiple events and creating relationships between them. So there's two kind of intuitive ways to combine events. One is with an AND statement, which you'll hear people refer to as an intersection when they talk about sets, or with an OR statement, which you'll hear people refer to as a union when you talk about sets. And the way I like to remember this is that when you make a union, you're creating something that's larger than the individual pieces. And you see that reflected in the images below. So in the OR statement, known as a union, you take the probability of event A and the probability of event B. And I know that's a little confusing. I use the word and instead of the word or, but you're combining the probability of the two events, including their intersection, which we're going to talk about now. So the intersection is associated with the word and refers to where both A and B are true. So where there's overlap between the two events. So those are the two types of relationships I wanted to go over. Now we're going to cover the concepts of independence and being mutually exclusive. So two events are independent. Again, I arbitrarily refer to them as A and B. If knowing something about one of the events tells you nothing about the probability of the other event. So there's a few ways to think about this, and I realize this mathematical notation can be really intimidating, but we're going to go over it, and the concept behind it is actually really simple, even if the notation is a little intimidating. So this reads as the probability of A, this line here says given B is equal to the probability of A. So this goes back to the example very early on in lecture where I was talking about flipping a coin, and if knowing the past observation told me anything about the future observation. So the fact that the coin landed on heads the first time gives me no information about what's going to happen in the second flip. And the second statement's the exact same thing. I just wanted to show that it goes in either direction. So the second event tells me nothing about the first event. Similarly, the first event tells me nothing about the probability of the second event. Right, that's the gambler's fallacy, is that people think that events are independent when they're not actually independent, and what happened in the past gives me no information about what's going to happen in the future. This is a more complicated formula, but the idea here, this is a really key rule that you'll use in calculating probabilities. I know you haven't seen this symbol before, but it actually did show up in the previous slide. We just didn't talk about it much. This is and this is or. So like this is A and B. So the probability of A and B, if two events are independent, is equal to the product of each of their independent probabilities. However, if they're not independent, it's more complicated. You take the probability of one of the events multiplied by the probability of the second event given the first event. This notation with the given is sometimes referred to as conditional probability. You don't need to know that. I just wanted to share like a formula that you can apply when you know two events are independent. So now I want you to think about these two types of scenarios that we've been describing throughout the lecture, coin flips and drawing from a deck of cards, and let me know if those types of experiments would be considered independent. So coin flips are indeed independent despite the gambler's fallacy, right? What happens in the past has no bearing on what's going to happen in the future. However, drawing from a deck of cards, the answer is it depends. If I draw from a deck of cards and then immediately replace the card and reshuffle, that would be considered independent. However, if I draw from a deck of cards, don't replace the card that I drew and draw another card, right? The probability associated with an event changes. So for example, let's consider the event of I get a red card. There's two color cards in the deck, red and black. If the first card I draw is a red card, the probability of the second card also being red is now slightly smaller, because before I had a 26 out of 52 chance of getting red. Now I have a 25 out of 51 chance of getting red. That was a little bit of a trick question, and it does depend on whether or not you're replacing the card and reshuffling the deck. Now I want to talk about being mutually exclusive, or which is also sometimes referred to as disjoint. A lot of people confuse this with independence, but they're very different concepts, and I think thinking about what the words mean kind of conveys that concept. So mutually exclusive really means they can't go together. This is some notation you've seen before. The probability of A and B is 0. And you can see that here in this diagram. There's no overlap between the two. There is no point in the entire sample space at which A and B occur together. Another way to think about it, if you think about the literal meanings of the words mutually exclusive, is it's either A or B or something else, but never both, right? It's one or the other. That's what mutually exclusive means. And that's very different than independence, where you're talking about the probability of the event having an effect on the other. And in fact, mutually exclusive by definition can't be independent, because if I know that event B occurred, I know what the probability that A also occurred is. It's 0, because they're mutually exclusive. It's one or the other. So by definition, they're not independent, right? Knowing one tells you a lot about the probability of the other. It tells you with 100% certainty whether the other event occurred or not. All right, so that's it for probability. This was a little bit of a shorter lecture. We'll start tomorrow with some of the inferential tests that you'll use for your analysis. And as a reminder, the very last week of class will be more rigorous. We'll cover multivariate regression. We talked briefly about linear regression, but this is going to be regression with multiple variables, because I think it'll be helpful for some of the project ideas that you guys submitted. Thanks again, and see you tomorrow.